When x is equal to 0, it looks like the mean of my data is right around 0. Just need a 0 there. Then I have to try to figure out the slope of this line. So, you know, I kind of sketched a picture, but the way I tried to draw it is that when x goes up by 10, y goes up maybe this point right here has y equal 5 or so, right? In other words, maybe when x goes up by 10, y goes up by 5, which would be a slope of 1/2. Okay, and that would be my linear regression equation. This is the case where the linear regression is best. I would say it is by far the best here because if the data actually looks linear, you don't want to use a tree because it's going to unnecessarily discretize, right? It's going to make all these flat lines instead of acknowledging that actually what you have is one continuous line. The spline is going to be too bumpy, but if you actually have data that follows a line, a linear regression is going to be best. Let me erase this part for the purpose of your picture. Okay. Okay. Now we're going to talk about multiple predictors. And as we start talking about having multiple predictors, we're going to stop talking about the spline. The spline, I mean, sure, if you run code for a spline and put in multiple predictors, it'll usually work. But is the spline usually a reasonable way to do that? It's usually not what you want to be doing. Never say never, but we're gonna focus on trees and linear regression as we get into multiple predictors. So let me show you a picture of one possible type of data set you might have, right? Let's say here's X, and maybe X can be kind of in this range, okay? And I draw 10 and 20 and a 30 for Y. And let me draw my data like this. Maybe I'm going to purposely draw some open circles here. You can do that in your notes as well. Maybe regardless of what X is equal to, we have these open circles scattered right around 10. So now I'm going to need a legend. Suppose that I actually have two predictors, not only X, but another predictor for east versus west, whatever I'm measuring, okay? And maybe these are people, and X is a political view, and the circles represent east or west. So open circle is going to mean east, and closed circle is going to mean west, okay? So what I've drawn so far is I've said, hey, for people from the east, X doesn't really matter. The Y value is always right around 10. Then I'm going to draw some filled in circles, and I'm going to do it like this. When you're from the west and X is negative, these are supposed to be filled in circles, maybe you get a value right around 20. And when X is positive, if you're from the west, maybe you get a value right around 30. Okay. All right. So let's see. If we are a tree, what are we going to do here? Well, we have two variables now. We could split somewhere on X, or we could split on east versus west, right? So what I'm going to do is I'm going to split on east versus west first. You could do it the other way, but I'm going to choose east versus west. So we're going to say east this way and west this way. And if you split on east, I don't think you also have to take into account X. The way I do this, it looks to me like once you know that you're from the east, you know that the data points are just arranged around the number 10 with a little bit of noise above or below 10. But X doesn't influence, doesn't seem to be related to Y, given that you're from the east. If you're in the west, though, it looks to me like X does matter. So I want to split again based on whether X is positive or negative. So I'll do X greater than 0 here and X less than or equal to 0 here. And the way I drew this, it looks to me that when X is positive and you're from the west, then my best guess is 30. And when X is negative and you're from the west, my best guess is 20. All right, that's what it looks like to me. So let's draw that onto the picture. So what this says is if you're from the east, then no matter what X is, my prediction is 10. If you're from the west, my prediction is either 20 or 30. So again, we're getting these discretized flat lines here. Okay, I'm not intending to make these different widths. There we go. Okay. So I think the tree's pretty good. That seems to go right through the data, right? Tree is best here. I didn't even compare it to anything yet, but the tree is going to be the winner. If you ran a linear regression that just put in both variables, let me show you what it would do. We're not done talking about linear regressions with two variables, but let me just show you the simplest one. So if I had some intercept plus some coefficient for x plus some coefficient for whether you're east versus west. So I'm reducing east versus west to now just a 0, 1 variable. If w is equal to 1, you're from the west. If w is equal to 0, you're from the east. So this is the simplest way to write down an equation, not the best way, but the simplest way to write down an equation that includes x and w. And the idea is I would try to choose some values for beta 0, beta 1, and beta 2 that would make this model fit the data, but it's not really going to work. So here's what you need to note. Note that when w is equal to 0, then this equation says that the mean of y given x and given that w is equal to 0 is equal to some intercept plus some slope times x. If w is equal to 1, this equation says that the mean of y given x and given that w is equal to 1 is beta 0, some intercept, plus some slope times x plus beta 2 times 1. So we have this extra value that we add on here. So another way to write down this would be some number plus some other number. So beta 0 plus beta 2 plus beta 1 times x. That's the same thing. So here's what I want you to see. I want you to see that if I compare this equation to this equation, they're both equations for lines, some number plus some other number times x, and the slopes of these lines are identical. So if w is equal to 0 versus w is equal to 1, both of those give me relationships between x and the mean of y with the same slope for x. It's just the intercepts that differ, right? When w is equal to 1, the intercept is a little bit different. It's different by an amount called beta 2. So the point here is that if I try to draw the line representing the mean of y given x when w is equal to 0, and if I also try to draw the line representing how the mean of y relates to x when w is equal to 1, those two lines are going to have different intercepts but the same slope. So now I'm going to go back to my picture. I'm trying to imagine how I'm going to draw two lines that have the same slope but different intercepts. In other words, two parallel lines, and try to go through these data points. And here it's just not going to work. Like, I can't think of a way to do it, right? So like this might be for the east, this linear regression, and this is for the west, right? And sure, like those black lines are kind of close to the dots, but they don't do it, because I'm forcing them to be parallel, they don't do a good job describing the data, not nearly as good as the tree here, right? Like the line for the east is not horizontal as it should be, and the line for the west doesn't notice the discretized pattern. This is not the way to go about this particular model. The tree wins here.